Okay, part 2 now, or B part of the optics lesson here is to talk about our flip side of our concave mirror is our convex mirror. So in other words, now this is our mirror that actually is curved out, so you can kind of see that it's curved out like this. So the shiny side is on this side, and we're actually looking at what kind of reflections or what kind of images can we produce by this. Again, the only type of image that we can produce with this one is a virtual image. Again, if you remember what it means to be a virtual image, it means that the object is going to be inside of the mirror. We'll actually see our image inside of the mirror. It'll look right side up, okay? It's not going to be upside down. So here we have our arrow, and our arrow represents our object. And our object, or our rules to drawing an array diagram, are going to be very similar. So we're going to take one, and there's got to be a focal point back here someplace. So this is going to be my focal point. There'd be a center of curvature, okay, out here some point as well. And the first ray is going to be the one that we're going to direct at the focal point, okay, so it comes at the focal point, and it'll come back parallel to our principal axis. The other ray is going to be parallel to our principal axis, and it's going to come back through the focal point, okay, on a line through the focal point. Now, this ray and this ray don't intersect, okay? Anytime we get two rays that don't intersect, that is a good indication that we have a virtual image. So what we do is we look on the other side of the mirror now to see where that image is going to be. So in other words, we take the reflected ray and we back it up. We take the reflected ray and we back it up, and we find the point where the two rays, intersect. And there's my intersection point that represents that. And so you can see that we're actually getting that image then inside of our mirror. Convex mirrors are used all the time. These are our big ones that we put up in like a store to see around the corner so we can watch people. They're the ones that we have on our rear or on our side mirrors. It says objects in mirror may appear to be closer than they are, okay? And so we always watch that. And again, it's the relationship here is that this type of a mirror will always shrink our image. So we generally see smaller images than what we get. We never get larger images. This, again, will only ever produce virtual images, so it won't make any difference where I slide this arrow. This arrow will always be at a point where it'll give me a smaller image. So my magnification is always going to be smaller. The same two formulas apply. So again, it's the distance of the image plus distance, 1 over distance of the object, and my magnification equation is just the relationship between the image distance and the object distance, or the height image and the height of the object, okay? So now let's maybe apply this a little bit. We should actually do something like, maybe we're looking for the focal length of this particular mirror. And we find that this length from here to here on the mirror is maybe 5 centimeters, okay? And maybe the distance from that we see this is from here to here is maybe 2 centimeters, okay? So we find that our distance of our image was, say, 2 centimeters. The distance of our object was 5 centimeters, and what we're looking for maybe is our focal length, okay? That's our question. Okay, so how do we set this up to solve this type of a problem? I'm going to set it up where I look at 1 over f is equal to 1 over my distance of my image is 2 plus 1 over 5, and now I have to do some math. Now I know how you guys are going to love doing fractions, but if you remember, adding fractions isn't hard. What you really need to do is have a common denominator. So in other words, I want to find what's the denominator that works with both 2 and 5. Now the easy thing is just take the 2 times the 5, and that gives me 10. So in other words, this is nothing more than 5/10, and this is nothing more than 2/10, and so I get a total of 7/10 when I add this together. Okay, which means now that my 1 over f equals 7 over 10, or I can reciprocal this and say that my f is now equal to whatever 10 divided by 7 is. Okay, and so that's how I can find my focal length. That would be in centimeters. Okay, so those are different things that I can do in order to find images with convex mirrors, convex lenses, or convex mirrors or concave mirrors. Okay. Now, if we go a step further with our optics, we're looking at converging lenses and diverging lenses. A little background information. Again, they're a lens, so they're a piece of glass, and typically a converging lens is any lens that seems to be thicker in the middle and thinner on the edges. So again, we have thick through here, we have thin through there. Now, when we look at this from a standpoint of what's happening with a ray of light, so in other words, here's my principal axis. If I send a ray of light this direction, okay, it wants to hit this glass, and here's my normal, it wants to bend. So I'm going to see the bending of my ray inside there. And then as I exit on the other side, I bend away because my optical property says going from more optically dense to less optically dense means bend away. So again, because of the way or the shape of my glass, I actually see a double bending of this, and I see my refraction that's going to force everything to kind of go in. So in other words, everything that comes into this lens is going to come back to a focal point, and that focal point is where I'm going to have things connecting, and that's a good thing. Okay, these are the same lenses that we have in our eyeballs, so our eyes have lenses that are similar to this. We use these in cameras, we use these in microscopes, we use these in telescopes. Okay, they're the type of lens that will focus something up and produce a real image. That's kind of the key thing, is we can produce a real image. Now, that's not to say that we can't get a virtual image as well, and we'll talk about when we get virtual images with this too. Before I go any further, I want to talk a little bit about how these are used to correct farsightedness. Now again, the issue with farsightedness is that you can't see things close up, okay? So you have a hard time seeing anything that's close to you. What it means inside of your eye is that your lens inside your eye is actually not focusing at the correct position on your retina. So it's actually focusing far of your retina. So you have to bring the rays of light closer together. So we use a converging lens to kind of shrink the rays up, bring them in a little closer. That way when they pass through our eye, it actually brings them back into focus on our retina. So it's about hitting the retina. Okay. Again, our same kind of policy falls through when we're looking at drawing ray diagrams. And by the way, I have 2 links to videos on how to draw ray diagrams, and I'd suggest watching either one of those. And we're going to draw some ray diagrams in your notebook too with this stuff. So my first one is that I have a line that's going to follow the principal axis. So I hit the principal axis, and when I refract, okay, I actually bend, and I should come out at the focal point. So anything that goes parallel should come back at the focal point. Okay. I should say through the focal point. So here's my F. There's my F there, and then I have a similar F on this side. The second one is one that comes down through the focal point. Okay. So we're coming down through the focal point, and it'll come back parallel to the principal axis. So now this one's parallel. This one came through my focal point. They intersect. Intersection's good on this side. Okay, now we're talking lenses, so we're on the opposite side, and that's where we want the images to form. And when we do a third one, if we wanted to do a third one, not necessarily needed, but if you went third one and you hit right through the center of the mirror on the principal axis, you're actually going to see that the refraction will bring us straight back on a line parallel, and that'll intersect, and so there we get our 3 points. And that points right there at that intersection represent that part of the arrow, so we can see that our arrow is now upside down, indicating a real image. So we can project this, and it does have a difference in its magnification. So we can actually calculate the magnification based upon the distance of the object and the distance of the image. I'm just changing those U's and V's to represent what I gave you in the equation as well. All right, so that's a converging lens. And again, if we adjust this object back and forth, we can change the size of this. And there is a point when we bring this inside of our focal length, we're going to have issues with trying to make our real image. So that's when we get into virtual images, is when we get inside that focal point. The last lens that we're going to talk about is a diverging lens. Okay, and the diverging lens is one in which it's thinner in the middle and thicker on the edges. Okay, and that's probably the one that we see most often when we're trying to correct vision. Most people actually have a nearsightedness issue. If you have a nearsightedness issue, you can't see things far away. Okay, and nearsighted just means that we're focusing before our retina, so we need to actually expand out the light rays a little bit so that we can bring them back closer to our retina. So a diverging lens does this. It actually spreads the rays of light out. When we look at this, we can only get virtual images, so we can never get a real image from a diverging lens, okay, only from a converging lens. So now my same thing applies. I have a ray that comes parallel to the principal axis, and as it goes here, it will actually refract so that it would be outside of that focal point. So here's my two focal points. So it'll come back parallel. And now, again, it spreads this direction, so we see everything going that way. The second one will actually go through the focal point on this side, and it'll come back parallel. So again, I have two rays on this side that are not intersecting, which definitely tells me that I'm looking at a virtual image. So I back up my reflected rays, so I look at parallel and I look at coming back through the focal point, and I see the intersection there of those 2 points, and that's where I'm going to get the image that'll form, and then it would be a virtual image. The third ray, of course, just goes through the center of my my lens on the principal axis, and so you can see that that actually intersects as well at that point. Again, we can look at these in terms of, we would see the image if we looked on the lens side of where the object is. So again, if we wanted to, we can look at the distance of our object, we can look at the distance of our image, we can look at, there is a focal length that can be calculated, and there's magnification that we could look at too as well. Hopefully that kind of covers everything. I wanted to kind of keep this a little brief. We're going to do two kind of setups. We'll do one with a mirror, a concave mirror, so we'll try to produce images with concave mirror. Then we'll use a convex lens, and we'll produce images with that, since those are the two that are kind of the fun ones. Other questions we'll address, and remember that we will be taking a test on Thursday. And again, I want to say that I have truly enjoyed the opportunity to teach all of you, and I hope that you've enjoyed kind of this class as well and would recommend taking it to other people. And there will be a survey that you'll be able to fill out. So anyways, this is the last video for the term. Signing off.